presentation about hive monitoring in general and the T2 in particular. We do the instrumentation with typically 3 devices per hive, a temperature and humidity device in the above the upper brood box, a temperature and SwarmMinder device above the lower brood box, and a scale under the hive. We transmit the data from the hive via BLE to a hub, and then from the hub to a cell tower and to the BroodMinder database. We can detect events like brood rearing. All is okay if we are in the brood zone, 92 to 98 degrees F during the summer months. And typically the temperature drops below or starts fluctuating 21 days after queen is removed from a hive. So we can tell if something goes on with a queen. We will follow along a requeening process. I'll show you how this looks like. We see swarming. A temperature peak in the brood nest typically is happening when a swarm takes place, and at the same time we have a rapid weight drop of the hive. We can see the colony size and population growth or shrinkage by comparing hive temperature versus ambient temperature. That's a very good indicator how big or how small the colony is, and this is also how Lorenzo, I guess, does his calculations for brood level in a hive. We can see robbing and other stresses, and that is manifesting itself with loss of thermoregulation. And what that is, I'll show you in an example. Let's talk about requeening. Here is an example where a hive was split on April 5th, and we have seen this over and over 21 days after the queen was removed. The queen was removed during the split, and pretty much 21 days after the queen removal, we see that the brood nest temperature starts to drop off, and then it fluctuates with ambient temperature. And what you also can see here, we have the red line is the temperature in the lower brood box, the yellow line is the temperature in the upper brood box, and there is more brood in the lower box versus the upper, and then as soon as the queen is gone and the 21 days are up, those two boxes pretty much fluctuate until we have steady brood again, which is in this case around the middle of May. So this is a full requeening. Beginning of April 6th, we removed the queen, and it took a good almost 1.5 months for the new queen to lay and the brood becomes stable. Now there are other events when you look at this, and you always have to keep an eye out, because there are these small nuances in these charts that you often overlook. And I've marked some of them here. There is something here, there is something here, and there is something here. Let's look at these one by one. This first one, that was a swarm. And if we overlay the weight chart with the temperature chart, we can see that there is an uptick in temperature and at the same time a drop in hive weight. And this is an indication, yes, that the hive swarmed. And it was a virgin swarm, because we removed the queen on April 5th, and on April 22nd the hive swarmed. So this couldn't have been a matey queen. It was a virgin. When we blow this up and look a little bit closer, we see that the weight dropped about close to 6 pounds in a 24-hour period. So midnight to midnight, the weight loss was 5.4 pounds. And we have the two temperature peaks in the lower box and in the upper box, and they coincide pretty much with the departure of the swarm. If we blow this up or put a line here, then we see that the bees start departing, and the temperature peak is actually potentially a little bit later than the swarm taking off. As I said, there are always other events, and if you zoom out a little bit, again here in the middle is the swarm event. And we have on the left, there is something strange going on. And we see a temperature peak here. We see the same thing right before the swarm, where we have a little dip in weight. We have this peak in temperature, and there's also a little blip in hive temperature. When I went there to look at this, we saw that the bees were actually hanging out in front of the hive and warming up the scale. And that was the reason why we had this temperature increase. and we had the weight increase in the middle of the day because they were just hanging out in front of the hive. And I'm saying all this basically because there are so many little things that you can see in the data that you quite often just overlook. All right, the next thing was, that was the swarm, and now we have this temperature event. That's the first time we are showing an event marked with a T, and that T comes from the T2 device, where events are automatically marked, if temperature events, if they are taking place in the hive. The T2 is a second generation temperature device with a more powerful processor allowing front-end logic, which means we can make decisions inside the device itself. We don't have to go back to the BroodMinder database. There is some logic and intelligence in the device itself that can trigger alarms and do certain things. The SwarmMinder is an upgraded firmware to include this event-driven logging interval, where we can change the logging period of the device from the standard 1 hour logging interval to a 1 minute logging interval in case we see a temperature event. And in this case, we can log at a higher resolution for later analysis of the data. This whole thing was built around a paper that was published in Europe, in Latvia, in 2016. And these guys outlined the swarm dynamics pretty detailed. And the way essentially this works, they are saying here that during the warm-up stage, in the last 10 to 20 minutes before takeoff, the temperature starts to rise in the hive. And they've come up with a logic to detect this temperature rise. The T2s flawlessly detected every swarm, but swarm season is over, and now we've seen a lot more temperature events that are not swarms, but that these are other things that are taking place, and which we need to look at this and potentially come up with an improvement for next year, because we have a lot of what we would call nuisance alarms. Now, the whole thing, the T2 SwarmMinder logs to a rolling buffer at minute intervals. It stores the logged values to the hourly log at minute intervals from 30 minutes before the event to 45 minutes after the event, once we know we have an event. Binary flags are set to alert that a temperature event is taking place, and this is used to send an email or a text message to the beekeeper saying something's going on. We also changed the transmission rate of the hub because it doesn't help if we have hourly logs and hourly transmission if we have a fast-paced event taking place. So we switched to 10 minutes once this flag in the T2 is set. And like I said, we relay either email or text message notification to the user immediately. Now, the history of this hive that I've shown, it was split on April 5th. We had a swarm on April 21st. That was a virgin. We found 2 more virgins in this hive when we looked on that same day. And based on this, the most likely next event will be the mating flights of the virgin queens, because they have to go get mated in order to be able to lay. Now, looking at this, we have the swarm, and we have this first temperature event on 4/24 after the swarm. This is now, here is a swarm, and here we have this temperature event, which looks pretty much like another swarm, with the exception that the weight loss was not permanent. The weight dropped and the weight came back. Based on this, if you would draw a line here, you could almost say, well, this is the natural daily swing that you see, but bees left and they came back, and I'm pretty sure this was the virgin going on her mating flight and coming back as a mated queen. They left around 12 and they returned to the hive around 4 p.m. It's the first time that we've seen this. We're quite excited to be able to detect such events. And the scientists that published the paper in 2016 regarding the connection, they did a tremendous job with 10 hives and 9 swarms, because they didn't have much compared to what we have today. We have hundreds of hives out there with this configuration, and we can pretty much invite everybody that has a citizen science kit to participate and observe these things by themselves. Let's look at some other hives and similar events that we've seen this spring. Dandelion Springs Apiary, that's my place in Chesterfield, Virginia. There's a hive in the backyard, and clearly, again, there's a weight drop, a swarming event, and the weight comes back, meaning it could be a mating flight. However, it did not miss the pattern because we think this was the first swarm, unless, of course, I missed the first one. That was March 28th, so it's quite early in spring. There is another one on April 6th. Again, the temperature peak, weight drop, and the weight comes back. The swarm leaves at 11:30 a.m., is back in the hive by 3:30. But again, it was the first swarm of the season, so it may not have been a mating flight, but something else. Maybe they left and didn't take the queen with them. We don't know. I mean, over time, we'll be able to explain what goes on. There is another one. This is, again, a weight drop and weight comes back. That was on April 12th. The reason why I don't have the weight continuing is because I had to strap the hive down right here where the node 5 is, because a storm was coming in and I didn't want the hive to fall over. But again, you know, we think that was a mating flight. This was the second swarm of the season, so it could have been exactly that. The next one, May 11th, a very classical one, leaves at about 1 o'clock, and about 2 o'clock, the swarm is back in the hive. We see the temperature peak. We see something else here, which, you know, we may or may not be able to explain. If I put a vertical line here for the timing, the temperature peak is clearly not before the bees leave the hive. The temperature peak is either at or after. And I want to, you know, go a little bit into more detail on this event because I personally witnessed what was going on. I received a text message on this May 11th at 13:19. I knew exactly what was going on because I knew which hive it was, and by then we gained some trust into the software, and I knew there was a swarm somewhere. So I went to get my bucket, and I saw the swarm in a tree right away. I mean, 4 minutes later, I walked outside. I saw them right there. I went to get my bucket to get the bees, and by the time I got back to the yard, that was about 2 o'clock. Well, the bees were back in the hive. They were in front of the hive, fanning, and they were marching back in. So I was pretty much witnessing a virgin leaving and coming back, and I found a virgin in the hive after that same afternoon when actually that was a mated queen, but at that time I didn't know because, you know, when you have a virgin coming back, the ovaries will not be developed and she still looks like a virgin. It's going to take a few days before she starts to lay. Here is another hive where we have high resolution data, where we ran the scale at minute intervals to really try and get a better feel for, you know, how is this timing thing. And what we see here is the hive starts to get agitated around 11 or 11:30. The wave starts to, you know, rumble. It goes up and down, and then they leave at about 2 o'clock. And the temperature peak is clearly after they've left the hive. So, you know, this theory about they're potentially warming up the flight muscles, it's becoming, you know, thinner and thinner. I don't think this is really the case. We see a 2.5 hour precursor to the swarm in oscillations in weight, but we do not really see anything in temperature. My theory is that this temperature event is really not caused by bees warming up the flight muscles, but I'm saying it's because there is so much disruption in the hive. The bees are just not able to maintain the brood nest temperature because there is so much going on. And I compare this to a situation where when a hive gets robbed out. That's a robbing event where you have bees in a hive and they're trying to maintain somewhat the temperature. The robbers come in over a number of days and all hell breaks loose. And there is no way these bees can maintain the hive temperature. So just to show you the parallel to the disruption that is caused by a colony being robbed. Let's go back to the T2. Here is another example of a hive that had 2 precursors to the swarm. So essentially 2 days in a row I had a warning, and then there was a swarm, and then we had 2 aftershocks. So all events, I think, were likely initiated by virgins. If you have a hive swarming, you have a lot of swarm cells, and sometimes the timing may be a little bit off, and these new queens start to emerge and they create havoc in the hive. And then you get patterns like this. We don't know enough to explain it all, but over time, I think, with your participation, the participation of the beekeepers out there, we will have a large data set, and we'll hopefully be able to answer most of these open questions. And it's our intention to, of course, make this available to researchers. This is our team: Sarah, Dwayne, Lorenzo, Rich Hogel, Mike Fowler, Amanda, Rich, and myself.